Hello everyone, and welcome back to Unit 4 in Geometry. This unit covers several more proofs than the last one did. So last time we were just learning a little bit about proofs, that was Unit 3. Now we're in Unit 4 and we're learning about proofs and triangle congruence. Alright, we're going to start with Section 1, which is called Polygon Congruence / SSS and SAS Congruency, and we'll learn what those abbreviations mean when we get to it. So we're going to go ahead and start with this little bit of information about polygon congruence. So we have geometric figures are considered congruent only if they have the same size and same shape. So I've already gone ahead and highlighted same size and same shape. I'm not sure how well it shows up on the recording, but they should be highlighted. Those two things are very important. Same size, same shape. And that's only if they're the same size and same shape. To prove two shapes are congruent, we need to show two very big things. The first one is that all corresponding angles are congruent. All corresponding angles are congruent. Alright, if one of them is angles that we need to show are congruent, the other one, if you think about it, in a polygon, you have angles and you have sides. So the other really big thing is that corresponding sides are congruent. Alright, so if we're trying to prove that something's congruent, again, all angles should be congruent, all sides should be congruent. Here's an example. If triangle ABC is congruent to triangle DEF, then we can say that angle A is congruent to angle D, angle B is congruent to angle E, angle C is congruent to angle F, and side AB is congruent to side DE, side BC is congruent to side EF, and side AC is congruent to side DF. Alright, now we're going to do an example. So I have example 1 here that says triangle ABC is congruent to triangle MON. Identify all pairs of congruent corresponding parts. So if we are starting with, let's just go ahead and start with sides. I notice that I have this right angle for angle B, and the right angle of this triangle is at angle N, and the short side over here goes from B to C, and the short side goes from N to O. So that's what I'm going to start with. So I have side BC is congruent to side NO, starting at the right angle and moving out. So make sure that you're starting from one angle on both times. They should be corresponding, and the angle you're heading towards should come second both times. Alright, so I have BC and NO. I'm going to continue going around in a counterclockwise direction here. So I have CA. So CA is congruent to continuing. So I went towards O, and now I'm going to go up the angle, OM. So CA is congruent to OM. And then AB is congruent to MN. Alright, there's all my sides. Now I'm going to go through and I'm going to write in all of my corresponding congruent angles. So we already talked about how the right angle is shown in B and N, so those must be congruent because they're both 90 degrees. So I have angle B is congruent to angle N. Then I headed towards C and then O, so C and O must be corresponding. So angle C is congruent to angle O. And then last but not least, we have angle A and angle M. So angle A is congruent to angle M. And I just noticed I drew a lowercase a that time, and our A should be capitalized, so I'm going to fix that. Alright, there's all pairs of congruent corresponding parts. Angle to angle, side to side. Alright, So now that we've done this, when we're trying to actually prove that two triangles are congruent, one very important theorem that we use is this third angles theorem on the bottom of the page here. And the third angles theorem says if two angles in one triangle are congruent to two angles in another triangle, then the third pair of angles must also be congruent. So if we're looking at this example here, if I knew right away that B was congruent to N and C was congruent to O, then that would mean by the third angles theorem that A and M must also be congruent to each other, and I don't have to prove anything else. These two angles are congruent, we have two pairs, so therefore the third is also congruent. We're going to be using that in our first proof of this unit. And this proof is the longest proof that we have seen thus far. We're going to go through and break it down, and then I'll talk a little bit more about what this means for us and what it will look like as you're trying to solve these proofs. Example 2 says, given that AD bisects BE and BE bisects AD, and AB is congruent to DE, and angle A is congruent to angle D, prove that triangle ABC is congruent to triangle DEC. Now, if you remember from what we just said on the last page, to prove two triangles are congruent, you have to prove that all sides and all angles are congruent. So I'm looking for 3 steps saying angles are congruent and 3 steps saying sides are congruent to show that these triangles are congruent. Now, that being said, we have a lot of information that was given to us in that section, and I'm going to go ahead and start by putting those pieces of our given statements in the first 2 lines actually. So I have, on my first line, I'm going to write out that AD bisects BE and that BE bisects AD. So it says both of those things there. So AD, and this is the symbol for it, it is an upside down capital T. AD bisects BE and BE bisects AD, and that is because it's given. Alright, next we're going to point out a couple other given pieces. So I have AB is congruent to DE, and angle A is congruent to angle D. So I'm going to put that in my second line. So I have AB is congruent to DE, and I have angle A is congruent to angle D, and that is also given. So from my given statements, I have angle A congruent to angle D, side AB congruent to side DE. Alright, next, I need to be able to prove all angles and all sides, like I said. So I'm going to start with angles. So if I already know AD, that's covered. Now I need to show that angle ACB would be congruent to angle DCE. And we are able to show that those two angles are congruent because we know that AD bisects BE and BE bisects AD. So we have angle ACB is congruent to angle DCE by the definition of, well, technically the bisector is helping us out here, but it's really the vertical angle theorem, and we know that because these are bisecting angles. So we're going to say the vertical angles theorem. Vertical angles theorem. Remember, THM is the abbreviation for theorem. Next, the only set of angles left is angle B and angle E. So I have that angle B is congruent to angle E. I'm going to put my markings on those. So angle B is congruent to angle E. Why do I know that? That's that theorem that we just learned. It's called the third angles theorem. I'm going to write that out here. Third angles theorem. I know that I can use this and that these are congruent because I already know two pairs of angles in these triangles are congruent to each other. Alright, so I have 1, 2, 3 angles. My angles are covered. Now I need to show that my sides are congruent, and I already have one of them up here, so I now need to show that AC is congruent to CD and CB is congruent to CE. If I can't show that those are congruent, then I can't say my triangles are congruent. But I think we can show that they're congruent. We're going to go ahead and start with AC and CD. So I have AC is congruent to CD. Why do I know that? Well, it's because we know that these two sides are bisecting each other. So by the definition of a bisector, or a segment bisector technically, we know that our sides have to be congruent because bisecting means that you're cutting into two congruent pieces. Alright, so if AC is congruent to CD for that reason, and we know that both sides are intersecting each other, then we actually know the next line already because it happens to be the same as this line. It's just on the other sides. So I now have CB is congruent to CE, and I know that because, again, definition of a bisector. And DEF with a period next to it is the abbreviation for definition in my mind, so that's what I use. Alright, so now I have 1, 2, 3 angles, 1, 2, 3 sides. Since I've shown all sides and all angles are congruent, all corresponding sets are congruent, then I can say from my prove line, which is where we wanted to go in the first place, I can say that from right here, triangle ABC is congruent to triangle DEC. Why? Because of the definition of congruent triangles. Alright, so now you might be looking at this and are thinking, every time I have to prove two triangles are congruent, I have to show all 6 of these things. This could be a lot. There's a lot going on here. This might be too much. Good news is, and maybe some of you saw already further down the page, we have shortcuts, thankfully, because those are long. So fortunately, we don't have to prove 6 things, 3 sides and 3 angles, every single time we want to prove triangles are congruent. We have 4 shortcuts that allow us to say that they're congruent after only proving 3 things. So our first shortcut is SSS, and that stands for side, side, side. It means that if we prove 3 sides are congruent in both triangles, then those 2 triangles are automatically congruent. And we don't even need to talk about the angles because this shortcut says that they're congruent. This is just a little more information about this. This pretty much just goes over what I just said. So if you can prove the 3 sides are congruent, you have 2 congruent triangles. Alright, let's go ahead and take a look at an example of a proof using side, side, side. Alright, in this example, this is example 1, it says use side, side, side to explain why triangle ABC is congruent to triangle DBC. Alright, and notice this is a lot shorter. There's only 4 lines here. And I know that I'm trying to prove that triangle ABC is congruent to triangle DBC, so I know that this is what my last line should be. So I have triangle ABC is congruent to triangle DBC. BC. Okay, before we didn't know what our reason was for explaining that. But this time we do, because we know that we're going to prove using the side, side, side theorem. So the reason for this to happen should be the side, side, side theorem here. And if you go back and look at that little section here, it just says side, side, side congruence postulate. So this is technically a postulate. So if we're being very exact in our proof here, this would be the SSS Congruence. I have to spell congruent right. Congruence postulate. Typically, you should not put this line in first. In fact, I'd say it's kind of bad practice to put this in first. But we know that this is where we're heading, and I want to make the point that this is what we're trying to do. So I'm going to put this in first this time. All right, so now I know side, side, side. So if I can prove our sides are congruent to each other, then I can prove that I have two congruent triangles. So I'm going to go ahead and back up here, and I'm going to start with what we know from the picture. So I have here A, B, B, D, and they have these tick marks that say that they're congruent. So I can say that A, B is congruent to B, D because it's given. Why is it given? Because there's tick marks in the picture that tell you that it's given. All right, so if I can do that for A, B, and B, D, I can do the same thing for AC and DC. So I have AC is congruent to DC because it's given. All right, there's one piece of this puzzle left. And in this case, it might seem a little silly what we're about to say, but you do have to state it this way, because when you're proving something, you have to have a reason for every little thing that you do. So if you remember in the last unit, we had a property that said something could be congruent to itself. That was called the reflexive property, and that is what's happening right here. So I have CB is congruent to CB by the reflexive property of equality. And most of the time I will just call it the reflexive property. Okay, here's why we have to do this. The reflexive property says something is equal to itself. So I have CB is congruent to CB, and you might be thinking, well, duh, it's one line. It is, but what if I wanted to split these triangles into two on this line? Does the line only go with one triangle? No, it goes with both of the triangles. So this line is actually two lines put right on top of each other, and they happen to have the same names. So I have to say that they're congruent to each other because they're technically two lines in two separate triangles. Because they make up this one line in the image, I can use the reflexive property to say that they're congruent. So now that I've shown that I have one set of sides, two set of sides, three sets, all sides, side, 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 I have proven that my two triangles are congruent using the side, side, side congruence postulate. That goes quite a bit quicker than having to show that all sides and all angles are congruent. All right, so that's one of our shortcuts. We have one more shortcut that we're going to take a look at today, and that is the side angle side shortcut. So I have SAS, and side angle side is what that stands for. Side angle side. And again, this is a congruence postulate. The side angle side postulate says that we need to prove two sides and their included angle are congruent. So when I say included angle, I mean the angle that is connecting the two sides. So if I have AB and AC, it has to be angle A because angle A is between the two sides. Same thing over here. If I have DE and EF, then I have to be talking about angle E because this angle is between these two sides. So you're looking for an angle sandwiched between the two sides. All right, let's take a look at an example. So I have example 2 here, and it says to use side angle side to explain why triangle XYZ is congruent to triangle VWZ. And in this picture, I already have a couple things marked for me, so I know those things are congruent, and I'm going to start with those pieces. So I have in my given statement here, I have XZ is congruent to VZ because they have the one single tick mark, and that's because it is given. The tick mark tells me it's given. And then in my next line, I have WZ is congruent to ZY because it's given. Okay, one second. Okay. Now that I have those two given statements, I need to think about what is missing from my proof here. So I'm trying to show that these two triangles are congruent, and I have this shortcut called side angle side, where the angle is between them. So if I have a side and a side, the connected angle is right here, it's angle Z. So I need to prove that this angle is congruent to this angle to show that these two triangles are congruent. So I'm going to write those out. So I have angle X, Z, Y is congruent to angle V, Z, W. Do I know they're congruent? Yes, I do. Why do I know they're congruent? Well, if these are congruent and these are congruent and they're bisecting, we have something that's forming right here, and those are vertical angles. So my vertical angles theorem tells me that I have two congruent angles, and because those angles are congruent, then I can use my shortcut and I can say that triangle XYZ is congruent to triangle VWZ using the side angle side congruence postulate. And I can use that, and I know that I can use it because once again I've proven sides, shared angles, they're congruent. Side angle side, side angle side. All right, this is where we're going to stop for today. We're going to pick back up in our next video lesson with our other two shortcuts that cover, well, we use more angles than sides, and I'll get to what those shortcuts are in our next video.